Hi students, welcome to the video on monostable multioperator. So we will analyze this monostable multioperator for a 555 timer circuit. So basically monostable multioperator means, so we know that there are two states for any digital output. So like state of 0 and state 1. So when I say state 0, it is 0 volt. When I say it is state 1, it is VCC. So this is uh, the two states of a particular circuit. So now when I say monostable multioperator, there is one state which is stable. Assume that it is there in a state of 0 unless I trigger the circuit. So unless I trigger the circuit, this remains to be there in this state. So this I'll call it as stable state. So this the state of the circuit is stable at 0 as long as I don't give any trigger signal. If I give a trigger signal, it goes to a temporary state of 1, that is VCC. So this is called as quasi-stable state. So this is quasi-stable state, means that this is going to a temporary state for a predefined time. After that, it again comes back to the stable state. So now, moving from stable state to quasi-stable state has to be initiated by a trigger signal. So I have to give a trigger here. So there is a trigger required. So there is a trigger required to take the output from stable state to another state where it is temporarily going to that state. In this particular case, it is 1. And after some time, so after a time corresponding to pulse width, so it will again come back to the stable state. So here it is called as monostable because out of two states, this state is stable. This state is stable, meaning if I don't give any trigger signal, so this remains to be there at stable state of 0. If I give a trigger, then it goes to quasi-stable state, remains for a predefined time, and again comes back to stable state. So this is the overall 555 timer, sorry, a monostable multi-operator operation. Let us take the example of implementing this monostable multi-operator using the 555 timer. So we'll just take the same 555 timer circuit. So I have put this whatever that is there within the box is the circuit of your 555 timer. We have three resistors of equal value R connected between VCC and ground. So this will establish a voltage of VTL and VTH at the inverting terminal and non-inverting terminal of these comparators. So this is comparator 1, this is comparator 2. We know that for analyzing the monostable multioperator, we need to give the signal. So the signal is given to pin number 2, which is the trigger signal, which is called as trigger signal. So pin number 2 is trigger signal. We are applying a trigger signal of something like this. So it will be a VCC voltage and it goes less than VTL for a predefined, okay, for small duration, and it will again come back. So now, as I said in the previous explanation, so we are supposed to give a trigger signal. This trigger, of course, I just indicated there's a trigger signal. So what type of trigger signal that you're applying for this implementation of 555 timer is, so if the trigger signal is VCC, if pin number 2, which is the trigger, if it is at VCC, it won't trigger. If you want to trigger, the voltage has to go below VTL. Suppose if this is your VTL value, if it goes below VTL, then this is called as trigger. So it will be get triggered. So once it triggers, so let it go back to the state of VCC. So now here I said you have to give a trigger signal. The trigger signal is given in the form of a low going signal which should be lesser than VTL, and again it should go back to VCC. So I have to apply a very small pinch like signal which is going less than VTL for a small duration, and it will again go back to VCC, so that now here you are disabling the trigger here you are enabling the trigger. So here you are not triggering, here you are triggering. So now if you want to again trigger, make the voltage go less than VTL, and then this is again the second trigger. If you want to trigger again, just give a trigger. Trigger means the voltage at pin number 2 should go less than VTL point. So that is the whole idea. Let us try to understand what is the process what we have. So now let us assume, let us take, this is V trigger, this is V trigger. So this is my time. So let me assume, so let us plot what is V naught and the capacitor voltage, that is timing capacitor voltage. You can see I have a resistor RT here, and this is my capacitor CT. So we know that this is my pin number 5, which is kept at 2/3 VCC, that is VTH, and I'm shorting 6 and 7. You can see this is pin number 6, which is your threshold voltage. Pin number 7 is discharge, which is connected to the transistor. And of course, this is pin number 3, which is the output. So let us start analyzing the circuit by considering the trigger signal as VCC. So this is my trigger signal VCC. So now let us see if the trigger signal is VCC, what happens. So now when I say this is trigger signal is VCC, you can see trigger signal is given to pin number 2. So this voltage is now, okay, let us assume that this is a 5 volt. So at this point you have 3.33 volt, and here you have 1.6 volt, because 1/3 of VCC is 1.66, 2/3 of VCC is 3.33 volt. So now when this is 5 volt, when the V trigger is 5 volts, so here just assume that here you have 5 volts and here it is 1.6, and here it is 3.3. So let us see what happens. If it is 5 and this is 1.6, so which is more now? V minus is more, so output voltage is 0 here. And since, let us assume that the capacitor voltage here is, initially 0 volt. If it is 0 volt, you have 0 here. So what you'll have? So you will have 0 here. So once it is 0, so what you have here? So if it is 0, so then this is 3.3 volt. So here it is, which is more now? So this is more than this, so this is also 0. So when you are saying that this is 0, so when you are assuming that capacitor voltage is 0, so capacitor is now discharging through this transistor. So now when this is 0 0, so let us assume that the output voltage is 0. So this transistor is of course this Q bar is 1. So when Q bar is 1, this is on. So our assumption of capacitor voltage 0 is valid, because when this transistor is on, it will going to discharge through this transistor to ground. So when your capacitor voltage is 0 volt, your output is also 0 volt. Output is also 0 volt. This is 0, this is now 0. So now output remains at 0. Capacitor is, okay, let me just write the capacitor voltage here. So let me say this is my capacitor voltage. So let me say this as V0. So my capacitor voltage is also 0. So this is 0 volt and output is also 0 volt. And as long as this is at VCC, as long as this is at 5 volt, this 0 0 condition remains. So your output remains in the previous state of 0 and 1. So this will continue forever. This I call it as stable state, because one of the state is stable. So as long as you don't give any trigger signal. So what do you mean by trigger signal? As long as the voltage is VCC, you're not giving any trigger signal. So let us assume that I'll give a signal which is going less than VTL. You can see I have a VTL voltage which is 1.66 volt. If the voltage at pin number 2 goes less than 1.66, so you can see now when this voltage is assumed that it is 0 volt. When it is 0, when this is 1.66, this naturally becomes high. So now this is high. The moment, of course, this is still 0. When it is 0 and this is 1, you can see now it will going to set the output. So now output immediately goes to VCC. The output immediately goes to VCC. When it goes to VCC, this becomes 0 because this is Q, this is Q bar. When Q bar becomes 0, this is now off. When this is off, the capacitor which was earlier discharging through this transistor is not able to discharge because this transistor is off. So now what does the capacitor will do? Capacitor will now charge towards VCC through RT. You can see now. So from this time onwards, the capacitor started charging. The capacitor started charging towards VCC. Now this voltage is no more. This voltage is no more 0. Now it has started charging. Let us assume that it has gone to 1 volt, 2 volt. So now what will assume that, okay, now this was 0, it was just there less than okay, VTL, and then assume that it again goes back to VCC. When it again goes back to VCC, does this again becomes 5 volt? When this is 5, this is now 1.6. So when this is 1.6, because this is always at 1.6, this is at 5. When it is 5 and when this is this, so will it not become 0 here? Because V minus is more than V plus, so this will become 0. This continues to be as 0 0 because this is continues to be 0 because this voltage has not exceeded 3.3. That is, capacitor voltage is still not exceeded 3.3 because it is still charging. So when my trigger signal goes from 0 to VCC, the output voltage remains as 1. So now how long this will remain as 1? So now you can see at this point of time, when this is 1, this is off, the capacitor is not having a part to discharge. This is keep charging. So this charging of your capacitor continues till the voltage of your capacitor goes above VTH. This, okay, now let us assume that there is a point which is, there is a level which is corresponding to VTH. As long as it is less than VTH, the transistor is off, the output is high, this continues. The moment it exceeds VTH, what happens to this? So assume that this is 3.31. Okay, assume that it is 3.4. The moment when this becomes 3.4, this is 1, this is 0, then 1 0 means the output will reset to 0. So now output has gone down to 0 because now this R is 1, this is 0. When that happens, whenever the reset happens, this becomes 0, this becomes 1. Now the capacitor will discharge through this transistor. You can carefully observe while charging, while this capacitor was charging to VCC, it was charging through RT. The time constant here, tau charge was proportional to RT and CT. Now just see what is the discharge path you have. Can you see this is the capacitor? Now it is discharging to ground through this transistor, but there is no resistor extra here. So now since when the transistor is on, the resistance is very less, so it discharges very quickly. You can see now it is discharging almost instantaneously. This is discharging very quickly. It won't discharge slowly as in the earlier case of your stable multioperator because there was a resistor associated with that discharge path. So since I don't have any resistor, so this discharges very quickly. You can see now. So now this was there in stable state until I give a trigger signal. The moment I give a trigger signal, the output has gone high. So then I have removed this trigger signal. When I say remove the trigger signal means I just made the trigger signal go above VTL. Whenever your trigger signal goes above VTL, so it's not a valid trigger signal. So meaning it will not trigger the signal. It will not trigger the monoshot. So when it goes to VCC, you are disabling the trigger, but output remains at a quasi-stable state of temporary state of 1 till what time? Till your capacitor voltage reaches VTH. The moment it reaches VTH and then it slightly crosses VTH, the reset will become 1. Whenever reset becomes 1, output goes to 0. This transistor turns on and it is now immediately discharging to 0. So this will be as 0 and the output voltage will also be 0 until I give one more trigger. The moment, suppose if I don't give any trigger signal, it remains as 0. It's a stable state. The moment I give the trigger signal here, the moment I give the trigger signal, this again goes to, okay, now this again goes to quasi-stable state, remains for the predefined time as it was defined here, and from that point capacitor again starts charging. So when it reaches VTH, it comes down, this also comes down, it continues. If you don't give any trigger signal after this, the output total is always at 0 voltage. So this is the operation of your monostable multi-evaluator. Okay, this is of course how the circuit looks like without the internal block diagram. So I have a trigger signal, so there is a stabilizing capacitor and there is a timing capacitor, there is a timing resistor. This is pin number 8, 4, 7, 6. 2 is the trigger signal where I am applying this type of trigger signal. You can see it should be between 0 to VCC and the trigger signal should be less than, it should go less than VTL. So then we have to find what is this pulse width, what is this T pulse width, that is for how long this output will be there in quasi-stable state of 1. So this will be in 0 state if you don't give any trigger signal. You can see now, suppose if I have a trigger signal which is like this. So this is my V trigger. This is my V trigger. If I make my V trigger as 5 volt forever, so this output voltage will be 0 volt only. Output voltage, this is my output. So this is my output. Output will be 0 as long as I don't give a trigger signal. The moment I give a trigger signal, this is triggers should be like, okay, just give a pinch. The moment I give it, the output goes to quasi-stable state. How long? Because now till here the capacitor voltage was also 0. Now capacitor starts charging. The moment when the capacitor voltage reaches VTH, the output comes down. The output comes down to stable state and immediately the capacitor will discharge to ground. Again, this remains in 0 state as long as you don't give a trigger signal. If I give a trigger signal again, what do you mean by giving trigger signal? Make sure that this trigger amplitude goes less than VTL. So once it goes less than VTL, at that point, the output goes to high state. How long this remains at high state? Till the capacitor voltage reaches VTH. Then till the capacitor voltage reaches. Once it reaches VTH, slightly extends, the output voltage again drop to 0, which is the stable state, and capacitor will immediately discharge to 0. So this continues. So this is my pulse width. So to take the output from stable state to quasi-stable state, this is a must. That is, a trigger signal is a must. Otherwise, the output will be always there in stable state. It will not go to this temporary state of 1, which is for a predefined time. We have to find the expression for this pulse width. It depends on what all parameters. So as we already know the expression for the capacitor timing capacitor voltage, so it's again the same expression we have to use. Vc of t is equal to V final minus V initial e power minus t by RC. This is a very general capacitor charging discharging equation. So since we have to find TPW, let me substitute T as TPW. So in order to find this pulse width, what is the final voltage during this? Okay, suppose if your capacitor is allowed to charge till infinite, so your capacitor will reach up to VCC. If it is allowed to charge up to infinitely. So what is the initial voltage? So at the beginning of your pulse width, the initial voltage is 0. So make it as 0. So at time t is equal to TPW, what's your capacitor voltage? It is VTH. So VC of TPW is equal to VTH. VTH. So what is R? R is RT. C is CT. So let us substitute all those things and then try to find out an expression for TPW. So is it now VTH is equal to VCC minus 0 e power minus TPW into RT CT. Upon rearranging, shall I write it directly as, so is it not VCC minus VTH is equal to VCC e power minus TPW by RT CT, or I can write uh, e power minus TPW by RT CT as equal to VCC minus VTH by VCC. So you can write TPW. Of course, when you make this positive, this will be get reversed. So can I write it as RTCT ln of, let me flip this. It is VCC by VCC minus VTH. This is my expression. Since we know what is VTH and VCC relationship, since VTH is equal to 2/3 of VCC, so does this become, so what is this? Is actually VCC by VCC minus 2 by 3 VCC. So this is actually becoming VCC by 1 by 3 VCC. So this VCC is what? So this will actually become ln of 3. So can you see now, is this actually becoming RTCT into ln of 3 is my TPW. So what is ln of 3? It's almost 1.09. This ln of 3. It's actually 1.098. So that's why TPW is given by almost approximately 1.1 times RTCT. So pulse width, that is this pulse width, depends on 1.1 times RT and CT. So because it is typically the time taken by the capacitor to go from 0 to VTH. So since RT and CT is the time constant parameters, so it is 1.1 times RT/CT is your pulse width of a monostable multivibrator in case of 555 diamond. So now let us try to demonstrate this. I'm having the same circuit rigged up there using analog discovery. So let me just show you the setups what I have. So this is already I'm getting the output. So this is my supply voltage for 5 volts and you can basically see I have a trigger signal of 100 Hertz of 95% duty cycle. You can see my off time is very less. Off time is very less, on time is more, and it is basically, you can see it is going from 0 to 4 volt. Okay, let me make it 0 to 5 volt. Okay, let me just make this 0.5 and then let me make this also as, so now basically what I have now is, so I have a signal which is 0 to 5 volts. You can see now this is typically a waveform what I expected, what I wanted here. You can see am I getting a signal something like this. This is 0 to 5 volt of very small off time, the on time is 95%, off time is hardly 5%. So this is the type of signal what I'm having here. That is applied to pin number 2. That is applied to pin number 2 of my circuit. So you can just have a look at it. Okay, let me show this also. So this is my pin number 2 and let me just show both the input and output. This is my scope. So I'm just separating the input and output so that it is you can have a clarity of this. So let me just slightly make it okay, -6. Let me make this, let it separate by, okay, let it be, okay, let it be 5, and let me just make this offset of maybe 1 volt. Let me just slightly move above. See now, this is the type of waveform that I'm having. Let me stop it here. See, the moment I give a trigger signal, so let me just expand this more carefully. Okay, let me just do this. See here, this is my trigger signal. So let me just make it 1 here. You can see when it is 5 volt. Okay, if you want to see the channel 1, which is my trigger signal, so this is 5 volt. When it is 5 volt, of course, this is the previous one. So when it is 5 volt, it is okay. Let me just do it again. So now, see, this is my trigger signal is 5. When trigger signal is 5, the output is there in the stable state. The moment when the trigger signal goes less than VTL, you can see this is 5. This is actually 0 here. So when it goes less than 1.66, the output has gone to high state. This output has gone to high state and it is remaining here for this much period. So by that time, the trigger signal has gone above now. So now trigger signal is now disabled and it has gone to 5. The moment this happens, it has gone to quasi-stable state. This remains in quasi-stable state till here. So what is this time? So this time is actually the time corresponding to your capacitor to charge up to VTH. So what I'll show you is, I will take out the trigger signal. I will just embed the capacitor voltage. So if I show you the capacitor voltage, you can see it is going up to VTH. So when it goes to VTH, I will show you this now. This is your capacitor voltage. Let me run it now. Okay, let me coincide them. So I will make this as okay, I'll make it as 0 so that you can see both are coincided, and let me make this also 0. Now what to observe here is, this is my capacitor voltage. Let me just do a single shot. Whenever your capacitor voltage, now this is where your trigger is applied. Now capacitor started charging. When it reaches VTH, the output is going down to 0. So that's what we said here. So what we said here is, whenever your capacitor voltage reaches VTH, output is going to 0. Exactly same thing is happening. You can see the capacitor is discharging so fast. So it is not taking any time to discharge because the discharge path resistance is actually 0. So there is no resistance involved in the discharge path except that transistor resistance, which will be very less. So that's why it is almost instantaneously dropping down to from VTH to 0, VTH to 0. So what to observe here is, so I have to measure what is my pulse width. What is my pulse width? So measurement I have to here is, so maybe only, okay, one of the measurement is, so channel 2, what is my pulse width? So maybe the period, not the period, the positive width. Positive width is the only parameter, because duty cycle, all those things are not valid. Even the frequency is not valid, because what we are worried is this. So the repetition period depends on how you're giving the trigger signal. So only this pulse width is of interest. And in channel 1, you can see what is your capacitor voltage. So maybe that we can measure it using the channel, sorry, the y cursor. Where is that y cursor? Okay, let me just okay, view, where is my y cursor? I can have this y cursor, take a normal one and then put one here, which corresponds to my 3.3. Can you see here? This is 3.33 volts, which is corresponding to my VTH. So my capacitor voltage reach VTH, and the pulse width, as far as this particular setup is concerned, so actually have 20K connected and it is zero point 0.1. So what is the corresponding value of your TPW? TPW is actually 1.1 times RTCT. So I have 1.1 into 20k into zero point 0.1 microfarad. So what I'm getting now is it is 1.1 into 20 exponential 3 into 0.1 exponential minus 6. So I should get 2.2 millisecond. So this is 2.2 millisecond is my expected value. I'm getting it as 2.018 millisecond. That's fine. Okay, this is what I actually got it, 1.1 RTCT, which is 2.2 millisecond. So I'm getting very close to it. So this is how we can able to conduct this experiment. And one more variation in this circuit is, so which is obvious. What we can do is, so we can actually change this voltage using an external voltage. I can use a V external. Instead of having this as 2/3 VCC, I can make it as V external. V external. So what will happen here? So it is not 1.1 RTCT. Now it is VCC divided by VCC minus VTH. So VTH will now become V external. V external. Supposing that if I make this equal to 4 volt, if I make this equal to 4 volt, what does this will become? This is 5 divided by 5 minus 4 is 1. So it leaves ln of 5. So what is this ln of 5? So ln of 5 would be 1.6. So let us do this. So let me apply a W2 wave gen and make the voltage as 4 volts, and let us see what is the pulse width. So it should be 1.6 times RTCT, that is it is now 1.6 into 20 exponential 3 into zero point 0.1 exponential minus 6. It should be close to 3.2 millisecond. Let us see how much will be that. So what I have to do now is I had to replace, I had to connect W2 using WaveGen. I had to connect an external power supply of 4 volts. So I'm just using the same thing here. So I'm using external another wire to connect to. So now this will be connected to pin number 5, where I'll be just using. Okay, I have connected. Let me just see. Okay, the moment I make it, this will go to 4 volt. So what I'll do, I will go here, I will use another channel. This also I'll enable. I will use a DC. I will use 4 volts now. I will use 4 volt. Now this is also running. This is also running. Let me just go to scope and then run. Just a minute. Okay, let me just see what has happened here. So channel. Okay, this is my wave gen. This is at zone, so all this offset has become now 0. This should be 4.2. Okay, let me make it 4. Why it's not? Okay, let me make it 4 volts. Okay, now this is fine. Okay, let me just check out what has happened. Let me just take out this. Something has happened. Let me just check out. So where is WaveGen 1? This is my WaveGen 1. WaveGen 1 is 95%. This is 2.5. Okay, my channel. This is, let me go to this. Okay, 1 second. Let me make this at -5. Okay, there's a loose connection. Okay, now this is fine. Now let me apply this second W2 and give it to pin number 5. Pin number 5 now. You can see now it has extended. Let me take out this pin number, sorry, channel 1 and give it to this capacitor charging, discharging, so that you can see that that is going up to VTH. Okay, now that is 4 volts. So what I'll do now is I'll take out this, okay, I'll make this offset as same 0 here. This is 0. Now basically what I want to show you is that when I make this, okay, let me just make a single shot. Just have a look at this voltage. Is it not 4 volts now? See here, my cursor. Is this not, of course, this is now 4 volts. See now, this is 4 volts. This is my, what is that? Wavegen voltage. This is 4 volts. And you can see the pulse width is now, of course, it was supposed to be 3.2 volts. You have it as almost 2.9. There's a slight error, so that's not an issue. But you can see now the capacitor voltage will charge up to VTH, up to VTH. VTH now in this case is external voltage, which is your this voltage. So this is my external voltage now. So whatever is this external voltage, that is your VTH. Suppose if I change that, so what I'll do now here is I'll just simply take out this. I'll place it here. I will just make this to come here and let me just keep running. Just have a look at this. Suppose if I make this to 3 volts, if I make this equal to 3 volt, can you see this is also coming down? Can you see this also came down to 3 volt, and you can see the pulse width also reduced the moment when I make this equal to 2 volts. Can you see when I make this equal to 2 volts, if I run it here, can you see has it gone to 2 volts? So can you see this has gone to 2 volts now? So this is almost 2 here. This is what is your Y cursor. You can see it is almost 2 volts, meaning whenever you change your external voltage which is connected to pin number 5, the VTH is not 2/3 VCC because it is now driven by this W2. So this whatever is your external voltage, that will be your VTH. So in the expression of TPW, when you have some external voltage, it is now RTCT ln of VCC divided by VCC minus V external. So it will not be 1 point, sorry, ln of 3. It will be a different value. So that care you have to take. So capacitor voltage will go from 0 to VTH. That VTH can be 2/3 VCC or it can be an external voltage. That's what you're supposed to do when you're doing the experiment. Connect the circuit. Of course, let me show you one thing. Suppose if your trigger signal is not less than VTL, what happens? So what I'll do now, I'll just take out this external voltage and I just taken out. So let me just remove this now. I will not have this. Now let me just keep running it. You can see when at the moment I remove it, it will go up to 3.3 volts. Now this is fine. So what I'll do now here is, let me take out this cursor also. Let me take out this for clarity. I'll just you can see now I'm having this is going up to 3.3 volts. So what I'll do now is I will make my trigger signal not to go below VTL. So I'll just make sure that offset is maybe 1 volt. Sorry, let me make the offset as maybe 4 volts or 3 volts. can see now when I make the offset as 3 volts, so okay, let me make it as 4 volts. So what I want to do is, okay, let me show you what is that I'm intended to do. I want to apply a trigger signal which is something like this. So I have to apply a trigger signal which is 5 volt and let it go hardly uh, 1 volt down only. Let it go up to maybe up to 2 volts. So because 1.66 is here, 1.66 is here. If it is from 5 volt to 2 volt only, if it is not crossing 1.66, then let us see what is the output is. It looks like a trigger signal. It looks like a trigger signal, but your VTL is here. Your VTL is here. So this is 1.66. This is 5. This is actually 2 volt. This is actually 2 volt. So how much is the drop here? So this is 3. So how do I set such type of waveform? Let me go here. So now I have to have it as offset of 3 and let this be amplitude of 2. This will make, okay, now amplitude of, see, where are you now? I think this is offset of 2 and amplitude of, okay, this is going up to, okay, if it is, okay, just give me a minute. So I have to have, let me make this amplitude of 1 volt and offset of 3 volts. Okay, this, let us see what will happen to this. Can you see now it is 2 volt and it is going up to, here it is, this is 2 volts and it is going up to 4 volts. So this is fine. Now can I make it 1.5? It is now 3.5. 3.5. This is perfect now. You can see now this is 2 to 5. So I have to have an amplitude of 1.5 volts. The offset is 3.5. You can see now it's going from 2 to 5. This is 2 to 5. Let us see how does the waveform will look like. Now this is the earlier one. If I run, the output is 0. I have applied a trigger signal something like this, but the output is 0. Why the output is 0? It's 0 because the trigger signal is not going less than VTL. The moment I make the amplitude 2 volts, you can see now, okay, what I'll do, I'll just run it now. You can see now, are you getting the output? Okay, let me just keep running it and show you if it is 1.5 what happens and if it is 2 what happens. If it is 1.5 it is off. If it is 1 it is off because it is at 2.5 volt and it is not less than, the trigger signal is not less than 1.6. The moment I make my trigger signal go less than VTL, you have your output. You can see this is even though this is 1.5 volt, which is less than 1.66, it is enough to trigger the monoshot. So the whole idea here is the trigger signal should be such that it should go less than VTL, otherwise it will not trigger the signal. And let us observe one more thing. Assume that if you keep giving the trigger signal repeatedly, assume that you are given one trigger signal, you are giving one more trigger signal, you are giving one more trigger signal. This is your first trigger signal, so output has gone high. The output will be high for a predefined time and then it will come back. these trigger signals will not be considered as a valid trigger signal unless this is going down to stable state. So in the stable state, whenever the signal goes less than VTL, that will be considered as a valid trigger signal. In the quasi-stable state, if you get few more trigger signals, they will not be considered as valid trigger signal. So what I'll do here is, so now let me just make this frequency bit more now. So let me make it equal to so and so. So now I'll show you this not with respect to this capacitor charging discharging. Let me show with respect to my trigger signal. So I'm keep giving trigger signal repeatedly. Let us see the impact of that on the output. Just give me a minute. Okay, this is fine. I will stop it here. I will just stop it here and then try to expand this and then try to show you what is the impact of this. This is now, see now, let me make it, that is too less. See now, here I have given a trigger signal. Can you see? Let me just make an offset of around -5. See now, this is my first offset, sorry, first trigger signal. When I give the trigger signal here, that is for the first time, the output was there in stable state. It went to quasi-stable state, and it is now, you can see it's remaining in state of 1 because your capacitor is not yet charged. So before that you are giving one more trigger signal. So since the capacitor voltage has not yet reached VTH, so this is not considered as a valid trigger signal. You can see now this is now coming down here. So at this point your capacitor has reached VTH. So now it goes to stable state and you are giving one more trigger signal here. The moment you give the trigger signal, it's coming up now. Let me just slightly increase the frequency more and try to show you what happens to this. Suppose if I make it 2 kilohertz, if I make it 2 kilohertz and then let me just run this and then stop it now. See here, this is your valid trigger signal. This is valid trigger signal. You applied one more trigger, second trigger, third trigger. These are not valid now. These are not valid here. So once it reaches VTH, the output has gone down to 0 here. Now when your next trigger signal comes after your output has gone to stable state, so then only the trigger is valid. So this is a valid trigger signal. This is a valid trigger signal, whereas this are not valid trigger signal, even though they are less than VTL. Why they are not considered as a valid trigger signal is because at that time the output is not there in stable state. The output is now in quasi-stable state here. So output is there in high state. Whenever the output is there in high state, it will not trigger again, meaning this type of monostable multivibrators are called non-retriggerable monoshots. Meaning when it is there in the quasi-stable state, if you are keep on giving the trigger signal, it will not start from here. The trigger signal or the pulse width will not start from here again. You cannot re-trigger it when it is there already in the quasi-stable state. That's why it is called as non-retriggerable. You can trigger it once, but you cannot re-trigger it every time whenever it is still there in the quasi-stable state. If you apply a trigger signal here, now this is valid because this trigger signal, your output is there in the stable state and it is now triggerable. But in this state, you cannot re-trigger it. You cannot re-trigger it. That's why the 555 timer monostable multi-operator is non-retriggerable monoshot. So this is non-retriggerable monoshot. Thank you.